Screening and Assay Development, and this session is kindly sponsored by TCAN. I think without those sort of sponsors, ELRIG couldn't run as a free conference, so that's very important. A couple of reminders before we continue. The first thing is don't forget your big quiz. Make sure you fill it in, hand it in to the front desk before Wednesday afternoon. In addition to that, there is the ELRIG Technology Prize and the Poster Prize. And the most important thing are your drinks tickets for this evening's wine reception. So before further ado, I'd like to introduce Ingo from Merck Serrano, and he's going to give us a talk on phenotypic HTS and validation with 3D cultures. Okay. Thank you.
Okay, first let me thank ELRIG for the invitation. And in the next 30 minutes or so, I'm going to present you a phenotypic screen, and I think interesting approach to identify starting points for disease-modifying drug development in osteoarthritis. And because when I tell people I'm working with Merck, this sometimes causes some confusion about the identity of a company. I start with shortly introducing my company. Then I go to shortly introduce the disease we are talking about, and then I'm going into some detail with the project as such. So Merck, in fact, has been founded in 1668 already. This makes us the oldest pharmaceutical company in the world. And in fact, originally we had a footprint in the US, which became independent after World War I and now is known as MSD or as Merck & Co. in the US and Canada, and that sometimes gives some confusion. We are the Merck who run under the name Merck in the rest of the world, and we are called EMD, which stands for Emanuel Merck Darmstadt in the US. We have a footprint in 66 countries. We are not a pure pharmaceutical company. We consist of 4 divisions, which I'm going to show you on the next slide. We have almost 40,000 employees and more than 10 billion revenues in the last year. So, as you might imagine, the largest division still is the pharma division, and the pharma division currently holds like 15,000 employees worldwide, and we account for more than half of the revenues. And then, of course, we have other important divisions. One you might know already from your lab work. Merck Millipore belongs to us, so you know at least the Milliq water, but they are much more than just producing Milliq machines. They are providing a lot of tools for life science research. Then we have consumer healthcare, which deals with OTC pharmaceuticals. Some of you might know Nazivin or Kyta and other stuff. And then, last not least, we have the high-tech chemicals. This is like pigments, and you have these color effect pigments, and some may know Magnum Gold, which is a Merck pigment. But most importantly, we are still market leader in liquid crystals, and almost any screen you see still has Merck inside. So pharma is just one of these 4 divisions, and how is research and development in pharma organized? So we are currently undergoing a reorganization, which is almost finished now. And now we have a couple of what we call TIPs, which stands for Translational Innovation Platforms. And these are organized a bit like biotech companies within the larger company. They have to provide a business plan. They have an independent advisory board, and they are measured by the value of the molecules they deliver for proof of confidence analysis. And then we have these central enabling expert functions, like, for example, us, the screeners, but also DMPK, CMC, and others, which serve as partners for these TIPs. We currently have 4 major TIPs. One, the largest still, is oncology. Then we have immuno-oncology, immunology, and neurology, which is mostly centered externally. And we also have a TIP which is a bit outside that organization, which is called Access to Global Health, which deals with the treatment of tropical diseases and access to treatment for poor people mainly. So, coming closer to the project I'm going to present, TIP Immunology centers around 2 what we call innovation clusters. That's indication areas. One deals with autoantibody-mediated diseases, and the other centers around osteoarthritis. So osteoarthritis is something not so many of you might have heard about already, but at least 10% of the audience, or hopefully not at least, but around 10% of the audience will experience this disease sooner or later in their life. So it's a really abundant disease. And it's a chronic joint disorder, and it's characterized by cartilage degradation, and you can receive a lot of pain, and the joints are getting less functional with progressing disease. And so far, a lot of treatments are out there, but most treatments really deal with relieving the symptoms, and it's not a really disease-modifying agent so far out there. And of course, one major aspect here is to stop erosion of the cartilage, which increases then, of course, friction of the bones, and regrow the cartilage. In general, having a joint already is a dangerous thing, because a joint is a heavy-duty construct and it's still very delicate. And so far, there are, as I already said, there are different options to treat progression of the disease. One, of course, is to stop the proteases, which degrade the cartilage, and to block inflammation. But that, of course, just stops progression of the disease. Of course, it would be also nice if we could strengthen the remaining cartilage, or even initiate regrowth of the cartilage. So, and the idea of the current project was so to have a look at the chondrocytes, which make out the major parts of the cartilage in the diseased joint, and see if you could find a means to trigger these chondrocytes to readapt a phenotype which could really fully function in the knee or in the other joints to produce new cartilage and to have a fully functional joint. And there are a couple of biomarkers which tell you that the chondrocytes are working nicely. So if the joint is diseased, the chondrocytes adopt a dedifferentiated kind of phenotype. They look more like fibroblasts than like normal chondrocytes. They have low collagen II expression, low Acumen expression, and also a transcription factor, which is a very good biomarker for healthy cartilage, called SOX9, is very low. And if the joint is healthy, the chondrocytes look very, very different. They have a very small phenotype. They produce lots of collagen II, lots of Acumen, and a high amount of SOX9. So the idea is to identify compounds which do exactly trigger the change of the diseased chondrocyte phenotype to a more healthy phenotype, meaning we would love to induce the round morphology again, which is something which you can easily see in the microscope. We want to support proliferation, because these diseased chondrocytes normally do not proliferate anymore, and they could not repair the cartilage. And then, as a second step, we would like to look at the biomarkers I just mentioned. Would like to see that collagen II production goes up, and collagen I production, which characterize the diseased chondrocytes, goes down, and also the inflammatory cytokines and proteases should go down. So how could we do that? It's difficult to identify a single target which could trigger all these effects, and also not so much is understood besides the protease and aggreganase situation in osteoarthritis. So we decided to go for a phenotypic approach, just start with diseased type of chondrocytes and see if we could get them to look like healthy chondrocytes again. So then, of course, question is which cell types to go for. And as Lorenz alluded already earlier today, it would be, of course, nice if we could go for primary cells, because these are unaltered. They have exactly the genetic equipment which should be present in the patient, and they should react like they should react in the tissue, and you could see something which is very similar to the natural situation, and you could apply diverse morphological and functional readouts. Also, of course, you see in parallel to the screening, you could also monitor specific or unspecific tox effects on these cells, and you see also some early ADME-like parameters. You see if compounds are rejected or if they are well absorbed by the cells, and so on. So, of course, the issue is talking about primary cells, and talking about an HTS, you need large quantities of cells. And also, if you want to do a screening, you need a quite homogeneous batch, which for primary cells can be a nightmare, because typically you can't work with one batch. You have to provide several batches, and they are pretty heterogeneous in most cases. So then, of course, the cells should be viable enough to be able to follow that switch, which I described before, to change the biomarker equipment and to change their morphology and to start proliferate again. And taken together, it was clear pretty soon that we would not be able to do this with human cells. So we would have to get diseased human cells, or maybe also start with healthy human cells from patients. And I don't have to explain you that it's really a pain to get such cells out of a patient, so this was clearly out of range. On the other hand, Germans are known to eat a lot of meat, and so every city has a slaughterhouse, and so Darmstadt has a very big slaughterhouse close by, and they produce a lot of meat. And you get it on the table in the canteen, but behind that there is something left over in the slaughterhouse that, as you see here, is the cartilage. And we decided to try to use this kind of cartilage for our screening approaches. So then, of course, you can't put a pig hip into a 384 well. There something has to happen in between. And no procedures were described, so we tried to isolate cells and bring them into culture, and we tried quite a number of sophisticated equipment, and everything was not really satisfactory. Then Christa Burger, who headed the project in these times, had the idea to go home to her kitchen and pick something like that. And in fact, this turned out to be the ideal instrument to harvest the cartilage. So it even was a used potato peeler. So it got sterilized, but it was a used one. So in the end, we had to buy several more because we had to deal with a lot of pig hips. So we collected this tissue, treated it collagenase, and then cultivated it for 7 days in an incubator. And luckily, already by the spread from the 3D situation to the 2D situation and the cell culture formation, these cells de-differentiated and adopted exactly the phenotype we were looking at. And of course, this was not completely unknown. Otherwise, we would not have started such an endeavor. So we could produce, luckily, relatively large stocks from these cells, and they were quite viable during a week of incubation, and we produced frozen stocks from these preparations. Still, those days, we intended to screen like 500,000 compounds, and that still means that we need quite a lot of cells. Luckily, we were able, during initial assay development, to reduce the amount of cells needed dramatically. So we are not talking about 10,000s or thousands of cells in a single well, but it's only hundreds of cells in a well. But that still means that in the end, we need hundreds of millions of cells. And that ended up with us harvesting cells from 30 pig hips, which was quite some work. And we produced frozen batches, and of course it's very nice to work from frozen batches because then batch-to-batch variability is lower, and what we did, we always pooled 2 batches at the same ratio, so we had a really homogeneous signal across the entire screen. So just not the time for that, to give you some snapshots on assay development. For this project, it turned out to be very important which plate type to choose. There's no rationale behind that, so it was not that we needed some sophistically coated plate or something. We just tested a high number of different plates, and we ended up that a simple Greiner plate in the end was very good and was the best one. We could use the cells for a number of passages, but their ability to differentiate and to proliferate dropped quite rapidly, so we stayed with passage 1. And then we played a bit around with a medium, so we had used ascorbinic acid, we added some insulin and selenium, and all that did not change the pharmacological behavior, and I will come to that pretty soon, what that means. And as I said, in the end, we were able to work with 250 cells per well. and culture volume was compatible with 384 well plate. So, of course, for this endeavor, no small molecule reference compound was available. And for screening, you want to define an assay window and you want to have a reference compound. So in the end, we used a growth factor for reference, FGF18. That, of course, is not the most ideal reference because it's not a small molecule. It does not behave identical to the small molecule, but it's the best surrogate we had. We also have to say that this growth factor is extremely efficacious. So we have to expect, if we use this growth factor to define the assay window, that we don't get a 50, 60, 80% efficacy response in primary screening. So we have to look at a relatively small response, and that means that the assay has to be relatively stable to reliably identify the true positives behind the background. So in the end, we ended up that we added compound 24 hours after seeding and then incubated the plates for another 24 hours. And here you see how it looks like if you simply titrate the FGF18. You see the cells adopt the round and small phenotype, which is known from healthy chondrocytes. And if you follow the biomarker I just mentioned, that also fits. So it really looks like FGF18, and that was also known, of course, can differentiate from our material of pig chondrocytes, again, the cells into chondrocytes, which show the equipment, are equipped with the proteins we would expect. So then initially we thought we would have to look at that at a confocal microscope, which of course is very throughput limiting in high throughput screening. And luckily we found out that we could also do a very simple analysis because of the really dramatic change in morphology between the cells, with the differentiated cells being much, much smaller. So we used a laser scanning machine, Acumen Explorer, many of you know or are familiar with, and we simply measured the diameter of the cells. So for counting the cells, we stained the nuclei and then we stained the cytoplasm and looked at the diameter. And here you see a picture which shows you the assay window. In the upper panel, you see that the undifferentiated cells are very, very small, and almost no cells are in the depicted window of larger diameter of cells. And if you differentiate, exactly vice versa. If you differentiate, the cells become smaller and rounder, and they appear in that window. And that was sufficiently stable to be measured for HTS. Here you see a snapshot of the HTS protocol. I have to make up for some time, so I don't go into detail. I already told you about the incubation procedure, so it's still quite complex. And we applied our standard HTS QC criteria and plates which were with a C prime factor below 0.5 we repeated. And in the end, we managed in a relatively short time to screen the 550,000 compounds which were available at that time. And then, of course, there was some disappointment with the team because there were very few hits in the end. But to be honest, this had to be expected. You know, you want to trigger differentiation and proliferation of a cell with a single small molecule. We don't have a cocktail, so we do single molecule screening. And that's, of course, it's still HTS grade. But still, in the end, we had like 25 hits, which had an effect, and 9 hits, which even gave an EC50 in the below 10 micromolar range, and all of these had no effect on proliferation of an irrelevant cell line and showed no toxic effects or other suspicious effects. So, and as I already mentioned, the efficacy of these compounds, as was to be expected, was pretty low. So the strongest had an efficacy of like 20% in comparison to FGF18. But as I said, FGF18 is a very, very strong inducer. So I just show you pictures of what the 3 best compounds do. You can also see that even though every compound induced this change in phenotype and also the changes in expression of the biomarkers, the cells do not look identical. So we have different series also out of this, and the effects are somewhat slightly different. We don't really know what that means in the end. And then, of course, we want to do some verification in further screening steps. And now we thought it would make sense to change to the human situation. And as I said, primary human cells are not readily available, so we screened a number of chondrogenic cell lines for expression of the biomarkers. And we completely failed with respect to SOX9 expression. All of the human cell lines, at least the engineered cell lines which are available, do either express no SOX9 or don't change SOX9 expression after treatment with FGF18. So we only found a mouse cell line, this ATDC5, which shows a growth factor inducible SOX9 expression, but we identified another cell line, a human cell line, SW1353, which shows IL-6 and MMP13 production upon induction by IL-1. And interestingly, it does it mainly in 3D culture. So this is also something which we came across. These cartilage cells behave more like in vivo if you keep them in 3D culture than if you keep them in 2D. And it's a general observation not only for osteoarthritis, we also see it in diverse oncology projects. If it goes to proliferation, cells have a tendency in 3D to behave more closely to the at least animal situation than in 2D cultures. So I have to be quick. We constructed a cell line from the mouse line I just mentioned with a SOX9 reporter measured by luciferase, and we could verify that, again, only the best of the 25 hits we had gave a response with an increase in SOX9 expression. And I can also shortly introduce how we did the 3D experiments with the other cell lines. We made use of the classical hanging drop. These days you can buy ready-to-use plates where you can grow thyroids in small droplets. And we did it also with the pig chondrocytes. And we see if you add FGF18, so if you differentiate the cells and bring them closer to a natural chondrocyte phenotype, they grow quite well. Without FGF18, they hardly grow in 3D. And if we compare different human cell lines, we see again that these SW1353 cells grow very similar to the pig chondrocytes. And out of interest, we also tried co-cultures where we tried to mimic the cartilage situation by co-culturing the SW1343 cells together with fibroblasts and macrophages and looked for expression of the biomarkers. And that's how it looks like. You see, again, here's a panel on the left lower hand of all the cell lines we tested. Some of the cell lines show expression of the biomarkers, some show not. Most of those which show expression of the biomarkers are not inducible upon IL-1, which should be expected. And the only one which remained was this SW1353, as I already mentioned. And very interestingly, and I don't go into detail because I know I'm late, in the lower right panel, you see if you look at the co-cultures of the fibroblasts, the macrophages, and the chondrogenic cells, you see they behave very much like natural cartilage. So they start, in this context, the 1553 cells start producing the biomarkers even without IL-1 induction. And they don't do it in 2D, and they don't do it if they grow alone. So it's quite an interesting model for further validation of the compounds. So that's already my last slide with content. We were able to produce a homogeneous batch for high-throughput screening with a phenotypic readout on 500,000 of compounds. And we were able to meet the standard data quality, and we had no compromises. So it really was, on a technical perspective, similar to a simple cellular assay like a flipper or something. So that was really surprisingly good. We set up some hanging drop culture for identification of cell lines which are useful for further analysis and set up the respective assays. And we also find out that it's hard to achieve reprogramming of cells by a single HDS-grade molecule. We have a very limited number of hits, but we found some hits which induce both the morphology changes as well as the change in biomarker expression. And we identified, as I already said, cells which we could use for further analysis. Now, please let me also thank the team, because I'm only the department head. I did none of the experiments myself. So Oliver Pöschke is heading our group for cellular pharmacology. Christa Borger is responsible for the lab, which did all of the wet lab work, and these guys are listed behind the end. And Carsten Peak was responsible for HDS screening, and the two guys on the lower right picture are our HDS staff. So, and that's it. I made up for 2 minutes, not too much, sorry, but thank you.